There are exactly 2 space stations in orbit around planet Earth right now. One of them you will have heard of, the International Space Station. But what about the other one? Tiangong, or the Heavenly Palace, is the 3rd in a series of space stations launched and maintained by the People's Republic of China. It has been in orbit since 2021, yet Western media reports much less on what happens aboard this second, enigmatic bastion hanging in space's expanse. So, what is going on up there? I decided to look into it, and when I found the list of their past and current experiments, and as I pieced together what it meant, the sheer scale of China's ambitions stunned me. We are familiar with the sorts of things being done on the ISS, experiments aimed at better understanding how humans might adapt to space environments and uncovering the mysteries of our universe and its physics, inevitably general in scope, reflected in the differing priorities and the emphases of each nation collaborating within it. But inside Tiangong, the goal is more focused. What is that goal? The answer might surprise you. I'm Alex McColgan, and you're watching Astrum. Join with me today as we uncover the goings-on within Tiangong Space Station and discover what implications this might have on the future of humanity in space. Unlike the ISS, which has been in orbit for over 25 years, China's own space station endeavors only started in 2011 with the launch of the first Tiangong space station. That's right, they launched the whole space station in one go. This was not a complex construction. Tiangong 1 was a simple tube-like prototype consisting of a sleeping and living station for Chinese astronauts, otherwise known as taikonauts, a habitable lab for docking and orbital experiments, and a module for propulsion. The whole station was only 10.4 meters long compared to the ISS 108 meters, and had 2 solar panels on either side. Its simplicity was a reflection of China's purposes for it, to master rendezvous and docking techniques, and to only dip their toes in the water of space habitation. Tiangong 1 was only in space for a little under 7 years. China did succeed in sending both crewed and uncrewed missions to Tiangong 1, and buoyed by this success, they upped their game with plans for a larger space station. To achieve this goal, more tests would be needed. In 2016, a second space station was launched, which also bore the name of Tiangong. Tiangong 2 was intended to field test key technologies that would be needed for the larger space station, and was deorbited just a few years later in 2019 once its tasks were completed. The road was paved for China's Tiangong 3. Tiangong 3, often referred to as just Tiangong, aims to be the home of thousands of experiments. To further this goal, Tiangong consists of the Tianhe core module for crew to live in and 2 science modules, Wentian and the Mengtian. The former designed to see space's impact on living things and to develop medical technologies, while the second focused on microgravity and its effects on fluid behavior, combustion, and more. Rotating solar panels connect to the station and turn to face the sun, allowing Tiangong to maximize its energy collection. The Tiangong has an external robotic arm that can carry a taikonaut to various parts of the station, allowing extravehicular activities to be carried out. The whole space station weighs 100 tons and is 55 meters long, and can house up to 6 taikonauts at once. Smaller than the ISS, but still large enough that it had to be assembled module by module in space, with modules launched between 2021 and 2022. Life on board the Tiangong is in many ways similar to life aboard the ISS. China tries to keep its taikonauts happy with a wide range of space foods, 120 different kinds. Naturally, given the muscle atrophying effect of microgravity, it's important for taikonauts to spend time each day exercising, or else they'd have a very bad time of things when they came back to Earth. Similar to the ISS, One of the main aims of the Tiangong space station is the popularization of science. So taikonauts spend some of their time taking part in presentations and collaborations with schools in China. For instance, this demonstration involving what fire looks like when there's no gravity. Students are also involved in growing rice seeds from the same batch of seeds growing on Tiangong, which will help Chinese scientists explore the impacts of microgravity on plant growth. Tiangong is home to several live plants, although some care has to be taken while watering them. Nothing so far here is too much out of the ordinary. However, there is a theme to the experiments being carried out on Tiangong over the course of its 15-year lifespan. 5 themes, in fact, that all point to a truly ambitious goal. The 5 research themes are on-orbit assembly and construction technologies in space, robotics and autonomous system technology, new energy and propulsion technology, environmental control and life support system technology, and new generic technology for spacecraft. The technical terminology can make things a little murky, so let's break down what each of these means. Even just the first of these areas of research is awe-inspiringly ambitious. By on-orbit construction technologies in space, we're talking about developing all the technology necessary to build large space facilities or even spacecraft. In a paper released in 2023, Chinese scientists laid out their goal to develop 3D printing capabilities and other manufacturing tools in orbit. They're already some of the way there. In 2018, they pioneered the first technology to 3D print ceramics under microgravity, which is appropriate for the nation that was one of the first to work with that material 10,000 years ago. Their desire to pursue this goal makes a lot of sense. Getting parts into orbit is a tricky proposition. The Tiangong space station itself had to be built over the course of several launches, with great costs involved, and with risk to delicate systems every time a module was launched. Imagine how much easier it would be if you could simply send raw material up and have it processed and manufactured into usable parts in space. Or even better, to use extraterrestrial materials already up there. The idea is certainly logical, but from the Tiangong's mission goals, it's clear that this has gone beyond the idea stage in China. They are looking for ways to implement it. The paper also describes inflatable scalable structures in space that could then be used as a habitat on neighboring bodies. These lightweight habitats, effectively tents on the moon, would be easy to transport, but aren't limited to the moon. More on that later. Robotic systems would go hand in hand with this. The manufacturing industry back home on Earth greatly benefits from robotic assembly lines. Chinese scientists and engineers are looking at ways robots can perform tasks in space, such as repair work, construction, cargo transfer, and more. Taikonauts are already laying the groundwork by testing robots and their ability to perform in microgravity, such as this test here, where a robot was run through this pipe. But it goes further than just plans for Earth orbit or even the moon. The next research area looks towards developing new forms of energy and propulsion systems. Solar panels are a great way to get electricity in space. However, China is looking into other options, likely because once you get out to the ranges of planets like Jupiter, sunlight is no longer strong enough. NASA's Juno mission is the furthest spacecraft to use solar panels to date, as I talk about in another of my videos here, but by that distance from the Sun, light levels drop to just 3% of what we get here on Earth. Hardly enough to support large projects out at that distance. And what this implies is that China is considering large projects at that distance, especially when combined with their aim to create efficient propulsion systems with a long operating life. Any rocket fuel propulsion system can get heavy on long trips, as you have to carry all the fuel you use, unless you can develop it in situ. Due to these increasing logistical costs, outposts that are self-sufficient are incredibly valuable, which is why taikonauts are also actively exploring ways to recycle oxygen, water, grow food, prevent microbial problems, and harmless degradation of waste. This is one of the reasons taikonauts are experimenting growing rice in space. They're also performing studies on the effects of microgravity on living organisms, such as fruit flies, to see how the conditions of space affect life. And just at the start of the year, taikonauts successfully tested a technology that brings oxygen recycling and the need for in situ rocket fuel together. In the first experiment of its kind, using a semiconductor catalyst, taikonauts on Tiangong produced oxygen and hydrocarbon ethylene out of carbon dioxide in an instance of artificial photosynthesis. Hydrocarbon ethylene can be used to make rocket fuel, but researchers also believe they could use the same process to make methane, formic acid, or even sugars, mimicking what plants do on Earth. This discovery is groundbreaking. On the ISS, the electricity required to recycle oxygen using electrolysis techniques is thought to take up a third of the ISS's energy usage. This new process is more efficient, gets rid of the CO2 being breathed, and can be done at room temperature. That's an incredibly useful technology to have on any long-distance space mission. Finally, taikonauts are testing their gear to make sure it works in space. This is the last of the 5 research themes, and while not as flashy as the others, it's a vital step in the process, and one that's difficult to replicate on Earth. The unique conditions of microgravity can put a lot of different strains on machinery. For one example, fluid dynamics are much harder to currently model, for another. And if you want to solve these things, it's practically impossible to replicate microgravity if you're deep within our gravity well. Putting it all together, it becomes clear that China is already thinking very carefully about not just a lunar base, but a vast network of habitats across the solar system, self-sufficient, able to mine resources wherever they are, and with the manufacturing capabilities to construct parts or whole new spacecraft out of it. With this infrastructure and technology in place, China will be able to mine resources from asteroids across the solar system and set up human presences on countless moons or planets. Yes, it's still early days, and it's not like China is alone in this, but it's a sign of how far things have progressed. If China is testing out the technology to build manufacturing bases in space, the platforms themselves can't be that far behind. To be clear, China isn't trying to be secretive about any of this. In fact, the Chinese are very in favor of collaboration. However, under American law, American astronauts are not allowed on board Tiangong without express permission from Congress, something not likely to be given. And although Europe initially planned to collaborate with China, they pulled out in 2023, citing insufficient budget and no political green light. Although European and American nations are wary of it, China has invited scientists across the world to perform joint experiments on the Tiangong station in a spirit of international collaboration and mutual benefit. It remains to be seen whether other nations will join China in these experiments, or whether taikonauts will be doing these thousands of experiments on Tiangong alone. Artificial photosynthesis, orbital construction facilities capable of building a space rocket, robotics, in situ rapid growth of food, new power sources, new propulsion. All in all, we are entering into a new stage of space exploration. To date, the furthest a human has ever traveled from our home planet is our moon. We've set foot there, looked around, but soon came home again. China's experiments on Tiangong are signs that a new approach to space is fast arriving, one where humanity does not simply go to space to come back again. We as a species are well on the way to leaving the nest of our Mother Earth and spreading our wings to fly out and discover new territories, further and further onwards from there. I hope we are ready for all that entails. "400 kilometers away from you, there is a laboratory whose results no other lab can replicate. Those results do not fit with our day-to-day experience, as in this lab, even time itself runs differently, slower than anywhere on Earth. That's because this lab is the International Space Station. And in this video, we'll see how even the most mundane of experiments have surprising results up there. But how is a laboratory even built in outer space? How does the human body survive there? And once the station's life is lived, how do you bring such a mega structure down from space safely? I'm Alex McColgan and you're watching Astrum. Join me today as we celebrate the ISS, a place where science and exploration transcend borders. The idea to have an orbiting habitable station in space has concretely been in our imagination since 1868. The American author Edward Everett Hale wrote about the Brick Moon, a space station made of, bog standard bricks. The US began taking the idea seriously in the 1950s, and then, in 1984, Reagan gave the presidential order to build the ISS, which, since its launch, has been a marvel of scientific discovery. Over its decades of operation, the ISS has not only expanded our understanding of the universe, but also demonstrated the power of unity in the pursuit of knowledge, which is an incredible achievement, given that its genesis owes much to a time when the Earth was a button press away from nuclear Armageddon. War has led to technological developments that seemed impossible in peacetime. Radar, jet engines, computers, nuclear weapons, and Marmite were all developed through a desperate war effort. A nation's fight to survive is perhaps one of the greatest motivators for technological advancement, and since the Cold War, despite no shots being fired, was no different because it pulled the trigger on the space race. But what about the times where there is no finish line? When there is no enemy to be conquered? Well, we wonder. Incredible scientific discoveries are also often made when scientists are left to be curious, left to ask questions that sometimes seem to have no useful answer, and left to actually collaborate. That is how the idea for the International Space Station was born. The ISS was conceived after the ambitions of the USA's Freedom Space Station and the Soviet Union's Mir 2 were shelved, at a time when space spending was no longer justified by either government now that the space race was over. The ISS program today has the involvement of 13 other member states, including Canada, Japan, the UK, and other European countries. The ISS is a huge structure by any measure. Spanning 108 by 73 meters, it would just about fit inside a football pitch. It weighs a staggering 450 tons, and with an estimated cost to date of $150 billion, it's worth nearly 5 times its weight in gold. Clearly, it was never an option to launch all of this in one go, a move that would have been both impractical and extremely reckless, so the ISS was planned to have a modular structure, one to be assembled in space, piece by piece. Each module was designed and built by a member state, before being launched into orbit on one of 3 vehicles: America's Space Shuttle System, or Russia's Soyuz or Proton rockets. Remarkably, every launch carrying a component of the space station delivered successfully, numbering 40 to date. There have been delays and mishaps, of course, and some resupply launches have failed, but if a component made it to the launch pad, it is now part of the space station. The orbiting megastructure that we're familiar with today is comprised of 3 main sections. The backbone of the station is called the Integrated Truss Structure. It is unpressurized and uninhabitable, but it supports much of the functionality, storage, and equipment on the space station. The ITS was designed to bear 4 huge pairs of double-sided solar arrays, capturing light from the sun and rays reflected from the Earth, which can generate 248 kilowatts at peak. But the ISS can only generate electricity for 45 minutes per orbit, so the station requires batteries to power the system while the sun is eclipsed by the Earth. Much of the power usage on board is ultimately transformed into heat, so the station needs large radiators capable of discharging 70 kilowatts of heat into space in order to safely regulate the temperature on board for its inhabitants. Below the ITS, the space station is divided into 2 pressurized and habitable halves, the Russian orbital segment and the United States orbital segment. So, how was this all built? Where would you start? Let's watch several key stages of construction to understand how the whole can be built. The first module put into orbit was the Russian Zarya module in November 1998. This module featured 3 docking ports ready to accept the future modules and solar panels to provide the station's first power source. The next mission launched later that year from the John F. Kennedy Space Center in December, carrying the Unity module. The docking of Unity to Zarya would mark the beginning of a new global space age. Inside the space shuttle, the Unity module was equipped with 2 pressurized mating adapters, or PMAs, that interface the American ports to the Russian port and to the space shuttle's ports. The space shuttle was fitted with a robotic arm called a Canadarm, which could attach to the 12-ton Unity module and position it above the space shuttle's docking port. This movement had to be done extremely slowly. Once aligned, the shuttle's thrusters were fired to engage the ports. When Zarya was reached, the Canadarm was again used to reach out and grab the Russian module and guide it towards the PMA on the Unity module. When it was in place, the thrusters were carefully engaged to make the connection. After a few checks, the joint space station was released after 2 weeks of maneuvers. With only these 2 modules, the station was uninhabitable. But that changed in July in 2000 with the launch of the Zvezda module from Russia, bringing life support and living quarters for 2 astronauts. Later that year, the Z1 truss module was connected, ready to join the habitable orbital segments to the ITS. And that November, Russia launched 2 cosmonauts and an astronaut, Yuri Gidzenko, Sergei Krikalev, and Bill Sheppard, to the space station to become its first inhabitants. Their docking marked the last time that the space station would be uninhabited, and a crew has been on board every day since. For the first 4 months until the first laboratory module named Destiny was attached to the space station, the astronauts were methodically commissioning the station's key systems and assisting with the delivery of further modules. In April 2001, an incredible tool was delivered by the space shuttle that could be used to maneuver objects in space without the need to complete a spacewalk, called a Canadarm2. It was the successor to the robotic arm aboard the Space Shuttle Endeavour. It could be attached by either end at specific power data grapple fixtures across the station. This means that the arm had the incredible ability to walk across the station to different locations to assist wherever there was a PDGF. A future Endeavour mission in 2022 extended the utility of Canadarm2 by delivering the Dextra, a telemanipulator, essentially giving the Canadarm2 a hand. Over the next 10 years, modules were continually added, including 5 more laboratory modules from Russia, Japan, Europe, and the US. Research aboard these laboratories is truly multidisciplinary, and the questions studied can span fields including astrobiology, astronomy, physics, chemistry, space weather, and space medicine. By the end of 2009, the last of the main solar arrays had been installed, meaning that the ISS finally appeared like it does today. But not all the planned modules made it into space. The Columbia disaster in 2003 led to the cancellation of some projects, including the artificial gravity module, a module that used centrifugal force to simulate anywhere from 0.01 G to 2 G for use in experiments. Artificial gravity has been a mainstay of sci-fi, and it would have been extraordinary to see humanity test its own systems on the ISS. Not least because the astronauts and cosmonauts would have appreciated it too. The absence of gravity on the station is a huge complication for day-to-day life. Almost nothing behaves as you would expect, ranging from the mundane to the deadly. Even the simple act of drinking a coffee made by the station's barista, the iEspresso, could be risky when you're surrounded by sensitive scientific equipment, zero gravity, and 100 laptop keyboards. A significant part of the station's research program has been on understanding the behavior of objects, fluids, and people in a zero-G environment. And if Trump's recently announced manned mission to Mars is to be successful, a trip that would take up to 10 months each way, it will stand upon the research of the ISS. Studies on the past crews of the station have shown how, in the chronic absence of gravity, the human body will ruthlessly atrophy any organ or structure that is surplus to its requirements. Organs are expensive to run. The musculoskeletal system in particular will degrade, bones weaken, and the heart shrinks. Careful exercise regimens must be planned in order for the crew to maintain bone density and heart function for their physical health. The ISS is equipped with a custom gym, so the crew can maintain some of their fitness. But despite all that equipment, it cannot fully simulate the coordinated strength and balance required to walk on Earth, and the astronauts effectively have to relearn how to walk on their return. The lack of gravity affects other organisms too. In space, even microbes behave differently. Aboard the ISS, zero-G has been found to alter the gene expression of certain salmonella pathogens that just so happens to have the effect of increasing their virulence, making them even deadlier. Well, I guess it could have gone either way. More immediate problems also present themselves in zero-G. Fire is of course dangerous in most situations, but on Earth, we at least have an intuition for how it moves and behaves. In space, fire can expand in any direction, because without gravity, there is no convection, and so the less dense hot air no longer rises. Flames in space can sit and persist, or even be invisible for lengths of time, because a low burn rate can be sustained by diffusion. Fluid dynamics is a crucial focus of space research, because without convection, even attempting to boil a kettle is going to land you in a pot of hot water. The nucleate pool boiling experiment was designed to study this exact problem, because without convection, how do you achieve efficient heat transfer in space? A kettle in space would be hampered by the formation of a large bubble at the heated base. Not that you would particularly want a hot cup of tea, because in this convectionless environment, the body cools less efficiently. So the atmosphere in the habitable areas needs to be well circulated. Other fluids need to be actively moved around in space by fans and propellers too, and, as is the theme, even these behave differently in zero-G. Fast-moving propellers can cause cavitation in a fluid, where a cavity is ripped open in the fluid and then explosively collapsed by the surrounding pressure. That collapse releases shock waves that carry large amounts of energy and can cause significant damage, meaning that propagation needs to be understood so that our equipment can go the distance on any space mission. Incredibly, research into cavitation in microgravity on Earth provided insight into the most explosive acts in our universe, supernovae. A previously unexplained supernova form has been linked to the collapse of bubbles in a fluid in zero-G under a process called eccentric core collapse. These experiments so far are all critical for the success of any future long-duration space travel. But the ISS runs powerful physics experiments too. In addition to the 6 pressurized laboratories, the ITS carries an experiment called the Alpha Magnetic Spectrometer, one that NASA considers as important as Hubble, and one that requires so much power and so much bandwidth that almost no other vehicle in space could run it. But what does it do? It's a detector, the business end of a particle accelerator. Space has cosmic voids with hidden objects that can generate particles with energies equivalent to a pitched baseball. Think about that, 240 exa-electron volts, millions of times more powerful than what our biggest accelerators can produce. Its stated aim is to research dark matter, specifically to search for evidence of a hypothetical particle predicted by supersymmetry called a neutralino. Moving on from the hottest particles in the universe to the coldest, NASA's Cold Atom Lab was designed to explore the quantum properties of matter and can reach temperatures of 1/1,000,000th of a Kelvin. It was the first to produce the 5th state of matter, a Bose-Einstein condensate in 0G. On Earth, these condensates eventually collapse due to gravity, but in space they float and persist. The crew has even been able to synthesize atomic bubbles aboard the ISS, a form of macroscopic quantum behavior. Long-lived BECs in orbit is a significant step, and they have uses. Atom interferometers that can be used to measure gravitational waves in a way that complements LIGO's capability. Atom interferometry using BECs would be able to capture the middle band frequencies of gravitational waves that LIGO cannot detect, allowing us to detect different objects and probe quantum gravity more precisely. The AMS isn't the only external experiment on the ISS. The Japanese laboratory module, called Kibo, has a facility known as the Terrace. In the vacuum of space, Kibo has been crucial in gathering climate data with sensors to perform atmospheric gas monitoring, ecosystem thermal imaging, and experiments with laser communications. It also features a hyperspectral camera to take images of the ocean around complex coastal areas. Typical cameras record in 3 bands, R, G, and B, but the hyperspectral camera records wavelength information across the entire visible spectrum, which, along with other data recorded, provides a rich dataset to understand the effects of climate change. Not only is the space station helping us to soar from the Earth, it is, perhaps more importantly, helping us to continue to walk upon it. The International Space Station is more than a scientific laboratory though. It is a symbol of what humanity can achieve when we cooperate and reach for the stars. As we look to the future, the ISS reminds us that the boundaries of exploration are limited only by our imagination and our willingness to work together. In the 2030s, the ISS will complete its final mission. In a carefully orchestrated process, the station will be deorbited, with its remains safely scattering across the Pacific Ocean. While its physical presence will be gone, the knowledge and inspiration it has provided will continue to shape the future of space exploration. The end of the ISS will mark the beginning of a new era in space exploration. Private companies like SpaceX and Blue Origin are poised to take on a greater role, while international partners are already planning next-generation space stations like the Orbital Reef and Lunar Gateway. The lessons learned from the ISS will guide these efforts, ensuring that its legacy endures. The International Space Station is an absurdly ambitious project that has stretched across decades, and we only skimmed its contributions to science in this video. If you would like us to dive into an ISS topic you would like to learn more on, let us know in the comments below. Objects tumble around in space. So have you ever wondered how the International Space Station stays upright? It's not just with thrusters. Watch what happens when this gyroscope starts spinning. Due to an effect known as precession, and a fun quirk of Newton's first law, a gyroscope is an incredibly stable object in space. No matter which way you knock it, it will always try to keep its orientation. The fascinating thing is that the International Space Station utilizes this effect in an array of counterbalancing gyroscopes to maintain its orientation in the sky. You may have heard me mention the Artemis program on this channel, the ambition of NASA to get a human colony on the moon and eventually on Mars. A big part of this venture is Gateway, a joint effort by NASA, ESA, Roscosmos, JAXA, and the CSA, the same space agencies that are currently working together on the ISS. And like the ISS, Gateway will be a space station, but not around the orbit of Earth, but instead around the moon. So how will it work? What does it hope to achieve? And why have a space station around the moon in the first place? I'm Alex McColgan and you're watching Astrum, and in this video we will investigate the Gateway mission and find out why it is such a crucial part of NASA's ambitions. This video is a special collaboration with the Robotitus channel and our own Astrum Spanish channel. If you are Spanish speaking, then be sure to check out their channels in the description below. The Gateway mission will coincide with the launch of NASA's new rocket, the SLS, or the Space Launch System. This rocket is the most powerful built to date, even surpassing the old Saturn V rocket. It is huge, and it has to be because NASA hopes to be able to launch 130 tons worth of payload into a low Earth orbit, with a smaller, yet still very heavy payload to even further destinations. This will be important because, as I mentioned, the end goal of the Artemis program is to get humans to the moon and Mars, and humans tend to need a little bit more to keep them alive than a robotic mission would. Launching all this life support into space means that not only has Gateway been designed to be a communications repeater for several deep space missions, but it will also serve as a pit stop. It incorporates a cabin module in which crews can prepare before embarking on other missions. However, unlike SpaceX rockets, which are trying to cut costs by utilizing reusable boosters, an SLS launch will be expensive as it uses disposable boosters. Combine this with the cost of research and development, and this could bring the cost per launch in the region of an eye-watering $2 billion. As such, the SLS has had its opponents throughout development, but regardless, they are committed now, and it's only a year away from its first voyage. Putting the arguments of cost aside, the SLS will be the most powerful rocket ever created by NASA. A true monster capable of sending a large amount of cargo into space with more power than ever. Just look at some of these tests they have recently run. One launch alone could get around 45 tons to Mars. The rocket's first task will be to get the Orion module, a human-ready capsule that will provide the housing needed to get a crew into space and back again, re-entering into Earth's atmosphere safely with a heat shield and parachute. The loading capacity of the SLS will not only allow the launch of Orion and its crew, but also some of the different modular components and instruments needed to assemble Gateway. As such, the construction of Gateway will be a long process, as they won't be able to launch the whole of it in one go. In fact, construction is not expected to finish until 2026, and that's only for the most basic and necessary modules. Fortunately, due to Gateway's modular design, possibilities to gradually expand the space station is a real and a likely possibility, depending on the needs of future missions. Although NASA have plans to get to Mars in the 2030s, NASA is also highly dependent on the budget it receives. So, while there are several missions proposed up until 2028, including several piloted missions, they depend on the success of the first missions and whether NASA continues to get the budget it's getting from the US government. At this point though, I can't envisage it not going ahead, barring total disaster, as China are hot on America's heels and have equally ambitious sights set on the moon and beyond. And America's efforts are probably spurred on by China's advances in space. we might have a good old-fashioned space race on our hands. Now, while this is done in the name of science, with the billions of tons of precious metals in space, and with the progress in technology space missions bring, you could certainly see this being commercially viable, as well as being important in a militaristic sense. And you can be sure neither party wants to be left behind on this one. Going back to Gateway, NASA intends to start with the basics, so the first phase of Gateway's construction will focus on installing the power and propulsion modules, to expand it later with the Halo module, which will be a very basic space habitat which will allow the stay of at least 30 days for a crew of 4 people. During the construction process of Gateway, NASA will send a rover to the lunar South Pole. The rover's special task is to map the location of water trapped at the bottom of the craters, so we can better understand just how much is there and to see how pure it is. This is because one of the proposed places for a settlement on the moon is around its South Pole, where the presence of water ice has been confirmed, hidden at the bottom of eternally dark craters, which protect the ice from the sun's rays. These craters could be perfect candidates for a possible habitat, as they would protect astronauts residing there too. The peaks around the craters, on the other hand, would be exposed to the most amount of sunlight, allowing solar arrays to capture energy from the sun more easily, for power and for the cultivation of plants. Remember, solar arrays wouldn't be so effective anywhere else on the moon due to its days that last a month, and 2 weeks in the dark isn't so useful there. Although we know from previous missions that water does exist at the bottom of the South Pole craters, we don't have a good handle on how much, as the lack of light there makes observations from space impossible. This is going to be one of the obstacles the rover will need to overcome. It will have to travel into a crater on battery power alone, and leave again before it runs out, so that the rover can charge them up again using the solar panels. The design of the rover is still pending, and in fact it will be picked as part of a design contest proposed by NASA to different companies. Once Gateway is built, NASA plans to launch the Artemis 3 mission, whose crew will be stationed at Gateway, using the Orion module to expand the space station's living space. Scientists will be able to study the effect on astronauts outside the substantial protection of the Earth's magnetosphere. During these short stays, they will test whether radiation exposure can be reduced to an acceptable amount. Also, as part of the mission, 2 members of the crew will remain in orbit in Gateway, while the other 2 will land at the South Pole of the Moon, where they will remain for about 1 week. They too will be expected to perform several moonwalks, again to examine samples of water ice and perform other scientific observations around the pole. It is proposed that included in this team will be the first female astronaut on the moon, although names have not yet been picked. The spacesuits they use will be a vast improvement over the Apollo counterparts. They incorporate a new design to grant much more mobility. If you remember the videos of the first Apollo missions to the moon, you will remember that the astronauts moved around very awkwardly, jumping around like rabbits. In this mission, they can walk and flex their legs. So thanks to this greater mobility and the use of modern cameras, we can expect a series of epic videos of these astronauts walking on the moon. Building on the Artemis 3 mission, NASA is planning to start construction on the moon itself to build a lunar colony that they hope will one day be self-sufficient. Everything that is learned in this colony in the relative proximity to Earth will be valuable experience which can be used eventually on the Red Planet. This includes oxygen production systems, water recycling, plant cultivation, and in general, making the rooms suitable for a long-term human presence. Going to the moon may be more economically viable than going to Mars, at least in the short term, because not only are the costs of sending something to the moon lower, but the moon can be a source of rare materials, for instance helium-3, which would be useful in a future nuclear fusion generator on the moon, and it might have more uses on Earth too. This element is exceptionally rare on Earth, and at one point it reached the price of $2,000 per gram. In addition, the moon could be used as a steel plant for the manufacture of metal foams. On Earth, this is achieved by injecting pressurized air into cast metal, but the process is tricky because bubbles can be produced that rise and explode, making the manufacturing of metal foams on Earth very difficult and expensive. On the other hand, in the low lunar gravity, this process would be much simpler, and the spongy structure of the metal much more uniform and of a higher quality. Once the material is ready, it is very easy to send it to Earth, since you don't need a large rocket due to the weak lunar gravity. One possibility is that it could be launched back to Earth with a magnetic catapult, something like a railgun, launching the order back to Earth or into orbit around the Moon to be picked up by a spacecraft later on. Again though, that's something for the far future. After Artemis 3, there are up to 4 more proposed missions, which will continue to expand Gateway as a hub for more lunar missions, but with the end goal looking to finally send humans to Mars. So, fingers crossed for the success of these missions. I feel like exploration is in humanity's blood, and these really are the new frontiers in this day and age. And with China pressing ahead with their own space program, we could be in for some exciting years ahead with regards to space exploration. Thanks for watching. I was honestly blown away by the numbers of you that signed up to the Patreon. Like I said in the replies to your DMs on Patreon, everyone here at the Astrum team is so grateful to have such an amazing community. If you haven't joined the Patreon party yet, we're still on our long-term 1,000 patron member drive, so you can go to the link in the pinned comment to become a part of that effort. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.